Welcome to the ASICS Hadoop architecture presentation. In this presentation, we want to talk about Hadoop architecture and the reason about building that architecture. What's the rationale behind the architecture itself? And that conversation is really important as you learn more about big data, because if you understand the reasoning behind the architecture and the decisions that you want to get, when you see more details, you connect those details with the decisions, instead of being surprised every time with something that it doesn't make any sense because you don't understand the rationale before. So let's get started. So as we know, Hadoop is a framework to solve for large data processing. It's helping companies to answer relevant business questions by looking into data that they were not able to process before. And this training is for anyone who is interested in understanding Hadoop architecture. And so as developers write a framework, the first order of business is to write down the guidelines. So those are the principles and the architectural goals that will help to keep the team focused in design. So as the work develops, they go back into that list to see and to solve conflicts between, to make sure that all the decisions are made to optimize for those goals. So if you look at these principles you listed here, you'll see that they are related with each other. If you can see the team, you'll find that these are coming from two main requirements. One is to process large amounts of data very quickly, and the other one is to use commodity hardware. So in this image, we try to represent the components of the Hadoop ecosystem and try to help you positioning each piece into that ecosystem. So as you know, Hadoop is written in Java. So the first level will be the Java virtual machine. And then the core components of Hadoop will be the MapReduce and the distributed storage. They're in blue. And those are the foundation to operating systems to distributed system. On top of this these core systems will be the data access languages that are Pig and Hive. And those languages enables you to write high-level programming, and that translates into whole level into Hadoop API. And they're very productive, being more and more used at the time. In the middle, you have the database. HBase means Hadoop database, and the idea is that you're going to create a cluster with a lot of machines, and they're going to be able to, if one fails, another one takes over. But they're going to be able to store key and value, say store for key 001 this information and retrieve that. So that's what HBase is for, and they have several use cases for HBase, including very low latency reads and also batch processing with the update requirements. That's something that HBase is really good for. The data tools from scope are tools that are related with either injecting data, so you have all machines outside your cluster producing data, and you wanted to have somebody streaming the data to your cluster so they are saved, because if the data is in HDFS, it's very reliable. It has minimum three copies of that by design. And also loading data from the cluster to another cluster or to a database, etc. Those are the data tools. And finally, the Zookeeper, it deals with the coordination. So the idea that the coordination for the distributed system is like, in a distributed system, you need one point somewhere that never goes down. No matter what, you will always keep the state is independent. It will always be the official truth of the system, right? As servers go up and down, independence if they're usable or not, you wanted to keep that state. So Zookeeper, the way that Zookeeper solves that is to create several servers using the same software. And anytime that you ask a question, they vote among themselves to see what's the answer. And as the servers go down and up, it's fine. They already have all the wiring and the software needed to wait until somebody's updated and just keep the people voting, the people that are ready to vote, etc., etc. And that's what Zookeeper does. So in this class, in this program, we're going to cover the distributed file system, the MapReduce, Pig, and Hive. There will be other programs to cover the other items, but those are the key components that allow you to build real applications in big data. So let's step back and take a look at why do we need a distributed file system, right? So until today, the I/O channels are still the bottleneck for quick reading. So there is a limit how much you can read and how much quickly for each one machine. So to process very large amounts of data very quickly, the easiest way is to try to put all the machines in parallel reading together. If you make a lot of machines reading in parallel, now you create a hard drive that is 10 times faster. If you make 1,000 faster, you create a hard drive that is 1,000 times faster. And that's kind of the idea of the HDFS, is try to spread the reads across several machines. So one of the things that the HDFS does is the inverse of the idea. The concept is inverse of virtualization, right? Virtualization, you're trying to have one computer, you try to make that computer appear like several virtual machines that are running in there. We're doing the inverse. We're putting several machines and we're trying to make those machines appear to be one big computer. And that's what DFS does. When you put machines under DFS, you're going to end up with one machine that simulates the capacity of all machines together, and also is reliable and auto-recover. So that's kind of the idea of the service, why is really important to have. And one thing that is important, once you have that structure, the infrastructure, you just keep adding machines. It is literally linear to add capacity to the cluster. You're just adding more machines and you make them faster. So HDFS and MapReduce are the two major components of Hadoop, as we talked about. And there is a pair, kind of a mirror relationship between them. They're taking care of different things, but they look very similar in a sense that they have one master and several workers doing the work for that particular service. So in MapReduce is the processing. So you have a job tracker that is taking, okay, this is a program that I need to execute, and I'm going to split this program in tasks, and I'm going to send to the task trackers and get them executed. And on the HDFS side, you have a name node that knows about all the files. I know the names of the files, I know the sizes of the files, I know where the blocks of the files are, but I don't return any information about the data for the files. That's the job for the data nodes. So in any cluster, we're going to have one name node and one job master, job tracker, and lots of task tracker together with the data node. So a job tracker is always paired with a data node. And the reason for that goes back to the idea that we wanted to move the calculation close to the data. So if the task tracker is running on the same machine, it's a local read. I'm not using the network, I'm just reading locally. And that's the Hadoop optimizes for that. So some of the attributes of HDFS are like commodity hardware. So we're going to use regular server hardware. Is fault tolerant and is ability to handle large amount of data, right? And one of the things that is like a trick that is used to optimize for these goals is the idea of streaming a file system. So in Hadoop, there's most of the time you're just reading large blocks of data, right? And that simplifies a lot on the I/O. If the architecture is always designed to be reading large amounts of data, then the disks are never jumping one side to another to seek for different places. They're basically reading that, read the next one, and so on. And that's one of the characteristics of HDFS. In the MapReduce, in the HDFS architecture that we looked on the previous image, you have the name node. The name node is the kind of the master. It maintains and manages the data node. It kind of understands where the data is, but it really only takes care of that directory information. The data nodes are the ones that are basically doing the job and of of storing the data, making sure that they talk to the name node saying that they are alive, and they're also serving to reads and writes for the data. So when you try to read, you read from the data node that has the data. Also, the name node deals with making sure that as you have all these files, and they have copies of these files, right? Because each file will be replicated. It makes sure that copies are recopied if you lose some machine. So it really helps to say, okay, I lost this data node, I need to recover, what do I need to do? That's another job for the name node too. So one important thing is, like, if you fail the name node, your cluster is unusable until you recover that. You can literally fail the name node as long as you have the backup for the metadata. You can restore that in another machine and your cluster is up and running. But if you lose that metadata, your data is literally almost unusable, because you're going to have a huge hard drive with a binary information that you don't know how to relate for. Now, on the contracts, data nodes can fail and recover, and everything is managed by Hadoop. You don't need any manual intervention. So there are two new concepts that we want to cover on this slide. One is the client. And the client is the client API, is a program running against a MapReduce cluster, right? So that is the API that we're going to be using to execute and to call, ask for executing jobs and loading data into this cluster, getting data out of the cluster if you need to, etc., etc. And the second concept is the secondary name node. So it's a secondary name node is a horrible name, was a mistake, but it's preserved because since the launch there'll be no change. There are talks about renaming that, but secondary name node is not a backup. The secondary name node is just a helper for the name node. So the name node maintains only the metadata about the data. It says, okay, I have this file A, it has 3 blocks, and the blocks are in those machines, and I have those servers are up, this one has a problem. So name node is basically looking just for that information. It has no information about data. But as the jobs progress, right, people start to, I need to create another file, I need to rename this file, I need to move this file to another place. All those changes are not integrated into the list. So name node has an index of all this information, and as the changes progress, they creates a list of changes that are happening. From time to time, he's just doing that. He doesn't have the time, and that's another guideline for the architecture, right? Name node is a single point of failure. So we wanted to do is a single point of failure is a place that's going to be very hot, and you increase the number of clusters. So if you put 1,000 clusters, everybody's going to be talking to that name node. So you want to do as less as possible there. And that's why the task of consolidating the changes with the index is made by the secondary name node. So the secondary name node gets, okay, this is the index, these are the list of changes that you need to apply. I'm going to do the consolidating for you. I'm going to build another index that has all those changes already organized there, and I'm going to send that information back. And that's what the secondary name node does. So a job tracker, so we'll talk about the sequence steps that you're doing a Hadoop processing. So each step is numbered, so you can follow the sequence by following the relationship about this component. So the first step is to copy the files into the HDFS, and then you start a job, right? You submit a job. So the client gets the information, and at this moment you start to split the jobs, right? So one of the things that the Hadoop needs to do is to, okay, I have those huge amounts of files, I need to break them into slices so I can run in parallel, and that's what job splits are. So after the job splits are, then there's a negotiation to say, okay, what are the machines that I need to run, right? And then the job tracker initializes each machine with the task tracker, right? And says, okay, I want to execute this task on this machine, that task on that machine. The criteria to select those tasks are, I'm gonna pick a server that has the data that I want to process. So if I need to process block 003, where are the servers that have the block? oh, they have 3 servers. Pick one of them, and that's one that I'm going to assign. Then once the job starts, or the master, so the job is composed by mapper and reducers, and we're gonna talk in detail as the class progresses. But just for now, just understand there's 2 types of jobs: the maps and reducers. So the maps are the ones that are based on the splits, and those are very parallelized, and the job tracker is controlling and allocate as many as possible. You have to remember there are other people using the cluster too. So sometimes you have, for example, 100 mappers, but you only have 20 slots allocated for you. So we're going to execute the first 20, then the next 20, and so on. So there is a capacity component on that decision making. And as the mapper executes, then it goes to the executes on the reducer phases. And in all this time, the task trackers are sending a heartbeat back to the job tracker saying, I'm up, and I'm processing. The job tracker also, independent of the task tracker saying that it's up, if the job is ending, right? If let's say that I have 1,000 tasks, 1,000 maps, and 940 executed, and I have now 5 that are really is low. Even if the task tracker is saying that is I'm up, the job tracker will add another duplicate for that. Says, okay, those guys are low, and just in case I'm going to create another one in another machine, and I'll pick the one that finished first, and then I ignore the second one. And that is called a speculative execution, meaning I'm going to just roll the dice and say, I'm going to ask the task for 2 people, because the data is in several places. I can ask the task for 2 people, and the one that brings me the results first, I'll use it. The other one, I'll say thank you and throw that away. And that's one of the techniques that the job tracker does to assure that you don't get one job that is slowing for some reason on that machine, and everything else gets blocked. And again, then the finalization is like once you finish the mappers, there's a process of sort. We need to talk that in more detail, and then the reducers are the final step. There's a final execution of reducers, and the output is produced in HDFS. So another thing that you need to understand is like input is coming from HDFS, and output is going to HDFS. Again, that idea that you don't want it to load anything directly in any single point. So one of the things that people, when start using Hadoop, really get in trouble is that they don't understand that anything that is distributed, right, is very powerful. It's like if you read anything, you're gonna have 1,000 readers. So you don't want to point the location that you're reading to any single point. So if you say, I'm going to decide to read from a database, load from a database. So just want to, let's say I'm loading just the list of states of a database. But I have 1,000 people reading at the same time, that database goes down. So any point in time that you have a distributed system, you have, as long as you're writing on inside of the cluster, everything is fine, because everything is proportional, right? If I have 1,000 clusters, I have 1,000 times 4 hard drives, and 1,000 to read, and 1,000 times 4 hard drives to write, or 4 or whatever number is the number of hard drives per machine. So everything is proportional. As the cluster grows, you continue to have that relationship. But if you point to a single machine or any small cluster, like a MySQL cluster to read or write, you can really disable those things very quickly. So is one thing to watch for. So the idea of replication, and in Hadoop they changed that in the versions, like, is the idea of hack awareness, right? So you have like several machines, they're grouped into racks, and you wanted to, one, maximize the chances of you never losing the data, but you also wanted to deal with speed. So the way that you do that, so if you pick, that's the standard replication. Replication means copies of the same block, right? So if you look at block A, I have a block A on line machine 1, on rack 1, machine 1, and rack 1, machine 2. And I have a copy on the second rack. So every single replication with 3 is going to be the first and second copy is going to be in the same rack, and the third copy will be in a different rack. The reason for that is if the rack 1 goes down, I have 1 copy out. And that's the rationale for that. At the same token, if I need to copy among the racks, if I keep the second machine, the second copy on the same rack is a lot easier. I'm not moving traffic around the racks, and that's the optimization that I want. I don't want to be always copying data from rack 1 to rack 2, right? I need to do that just in case. But if machine 1 fails, I have the copy on rack 1, I'm good. If the rack 1 fails, then I have copy at rack 2. It's less optimal, but I still get access to that. So reading in HDFS, right? You open an HDFS client, and then you try to get the block location. So you talk to the naming node that knows about the file. I need to read file ABC. Where are the blocks? And it says, look, blocks is block 103 on server 10, blocks 1020 on server 15, and so on. And then after that, I open connections to read directly to the data nodes, like we talked. So the name node function is just to provide where the data is. And all the connections to read are being provided by the data node themselves. The writing process is similar. The only difference is that I'm writing to one data node, and that data node is forwarded to the next guy. So it's basically I say I'm going to write to the first data node, and I say, and the data node already knows that I need duplication or 3 copies of that. So I'm going to pick 2 other guys, and I'm going to write to them and wait them confirm that it's written. So the first data node writes to the second says I need 1 more copy. So I pick another one, write, and wait for the third guy says yes, it's okay. The third return to the second return to the first, and then I return back says, okay, data is written. So when you receive the signal that is written in 3 places. That's something, but you have to remember those things are happening in parallel, right? The data node, the first data node does not wait until he finishes to write to invoke. He finishes that in parallel and keeps writing and so on. So at the end, when you receive the data back, everything is in parallel and you have written in 3 places. So this ends this initial presentation to give you an idea. If you get more information and for further training and discussion about the whole program, please contact support@azixia.com. Thank you.